Okay, so now I'll share my screen again, but now jump over to our MATLAB type stuff. All right, so this is maybe so my code's a little embarrassing here because I threw this together kind of quick. I gave you guys like 2 weeks to do this homework, and then I tried to do it in a few hours. So, but this gives you an idea of how you can approach it in MATLAB. You can do all this manually, but once you get good at MATLAB, you can go ahead and do it. So we're asking about the, you know, we're given this Hamming code that we talked about in class with these parity equations. Okay, so these are the ones that are commonly associated with this Hamming 743 code. So what's the code rate of this code? Well, really, you probably want to do B and C first in order to get this code rate, but it's this is the number of bits coming in. This is the number of bits coming out, right? So 4 is the number of message bits, 7 is the length of your code word, right? So when we look at that, so you know, K is equal to 4 from the specification of our code. We've got N, and then our code rate is K divided by N, and then we've got I create our parity equations. Okay, so I'm going to create a matrix that's K by 3. Yes. Elmer.
Brian has a question. What's
Right.
the on the Hamming code? What's the number 3 for it? What like parameter is that?
It's
M. And what does that do?
Yeah.
N minus K.
Yeah. And,
Oh, that's it.
yeah.
Oh, okay.
Yeah. Yeah. Okay. So so a lot of codes don't actually include that. Just kind of it's extraneous information, but by convention sometimes it's put in there. So all right, so we're going to generate this parity matrix that's K rows by 3 columns. Okay, K rows because there's K message bits in our input, and 3 columns because there's 3 equations that we're using. Okay, and so we have this by using these semicolons after each of these is really creating a column vector. Some people would like write it out as a row vector and then do the transpose of it. That might be a little neater notation. I don't know. That's personal preference. So we've got a 1, 1, 0, 1 because that's going to take that first bit, second bit, and fourth bit in that K sequence and do a modulo 2 operation on those, right? So and then similar for second equation, third equation. Now we can form our generator matrix by taking the identity matrix, which in MATLAB is an I of dimension K. Identity matrices are always square. So you just have to put this one dimension in. It's really going to be K by K. Since it's always square, we can just use K there. And then we add on, concatenate to the right, this parity matrix that we just created here. Okay. And then we can display that, right? So let's just run this whole thing so we can see it as we go. And so I didn't label my outputs very well here. So but there's our our K, our code rate, and that's our generator matrix right there. So we see that identity matrix, K by K, and then that's our parity checks. First equation represented, second equation, and third equation represented. Okay, now we can form our H of T, or H transpose, and then we can take the transpose of that to get H. Okay, so let's flip back to our editor here. So that gives our G, and then to get our H transpose, we create a different identity matrix. Okay, so this is a little bit tricky in that to get these dimensions matching up, you know, our parity check equations are 4 by 3, right? And so when we transpose that, it's going to be 3 by 4, right? So we need a little bit different identity matrix here. So that's, if you look in the lecture, that we use a lowercase m, which is equal to n minus k there, right? So, so we create that identity matrix, and I just call that m, because that's a notation we have. And then our H transpose is this, is a parity check. Then on top, right, here I have a semicolon, and that means that this other matrix is going to be added below, right? So your parity check, and then this new identity matrix down below it, and then we'll take the transpose of that using that the Matlab transpose operator, which is apostrophe, and then that'll display that H, right? So that we just looked at. Okay, and then we want to what's next here? Where are we up to? So write the parity check matrix. So we've done that. Now write the code words for each data message in a table. How do we approach that? I should rearrange my screen here, right? So let's try that. Except that. Okay, so yeah, we're down here now. So yeah, there might be a more elegant way of doing this, but I'm just creating our messages here from they're 4 bits long because k is equal to 4. So I'm just creating these vectors in a matrix, right? So that would be one message, the next message, another message, and so on. So I just did this in 2 lines, but basically we've got messages now added 1 per row. Okay, and then to get our code words, we're going to take those messages and multiply them by our generator matrix. Now, you know, you can do that vector by vector, okay, but with Matlab, it'll handle those matrix operations automatically. So I can generate the whole table in this one statement. When you start doing these multiplications, you know, you're adding also as part of that matrix multiplication. And so you might get values greater than 1 when you're adding these up, right? So we do a modulo 2. This is all modulo 2 type operations. And sometimes you don't have to worry about it because it can't get larger than 1. So I don't always have the modulo 2 operation in there, but so that's generating it. And then this mod comma 2 is doing the modulo 2 operation. And so now here we can see these are messages, right? So that's just you know all the different words. And then here's our code word table, right? So now we've taken these 4, and since it's a schematic code, you should be able to take each of these lines and see that message replicated in the corresponding code word. And then these other digits here, we're not actually seeing all 7 of them. now we are. So these last three digits in each of these code words are parity checks. Okay, so where are we at? Then in part G, I think you're asked to draw out the error mens, right? So this, we're going to use the syndrome decoding method. So we're looking at associating an error vector with each of those syndromes. Okay, so and we want the minimum weight ones, right? And so generally you're going to have a minimum weight of 1, right? And there's so I just kind of wrote those out here and created all these minimum weight 1 error vectors. And then there's that last one, and that one might have given you a little trouble because there's going to be one more one that's now a minimum weight of 2, right? Because we're starting with 1, we're not starting with an all 0. All zeros mean there's no error. And the math still works out, as you'll see. But so these are showing where we think the error position is.
Miguel, what? So you can't,
Miguel.
in the example, it started with all zeros.
Did it?
Mhm.
Okay. So, it's kind of by convention, yeah, that you could, the zeros is a legitimate, error, minimum error vector, but it's no errors, right? So, yeah, so that's okay. You'll see in my code, I handle those as a special case. Okay. And so, yeah, you could put that in there and that'd be fine. But you can end up with a minimum weight 2 vector then as an additional one. So if you use 0, you probably wouldn't get to this point, but this one typically matches your S syndrome of all ones. Okay. So so we can write out these in error mens, and then we can also generate. Oh, see, I moved that code, and now it's not going to work because it's trying to multiply that E men there by H of T. So I probably need to move it back down here. Okay, so let's run it again. So you should see here these error mens, and this last one, if you do it such that you're only looking at errors, vectors with errors, then you're going to have this minimum weight 2. This one's not unique. Okay, so there's others that can come up with that. And I just derived this one by inspection, but when you multiply this E men by your H of T, then that produces your set of syndromes. And so you should make sure that this one produces the 1, 1, 1.
So it's okay to have repeated syndrome because you have 1, 1, 1 twice in syndromes. And your 4th row and your last row.
Oh, you're right.
Which is
Okay,
you start with all
so,
zeros.
yeah, see, I did this too quick, right? So, yeah, so, you're right, that one is, so I probably, so you could include the 0, 0, 0 in there also, and that would satisfy it, so. Okay, I'll have to go back and check with that, there's I did most of this notation out of this, textbook, second reference on the textbook and stuff, so, all right, so, real quick, you then can have this set of syndromes that are possible, and then you can get your message by multiplying the K, the message bit by the code word and the generator matrix, I'm sorry. So here we have, I'm picking off the particular message in my array that corresponded with what the question asked for, multiply it by G, doing a mod 2. I do, and then I do this MATLAB trick where I just sum across the vector, and that's my weight. That's the number of ones in it. I just do it again for the other one, and then we look for the Hamming distance. There I do an XOR between the two, and then again I sum up those number of differences in it, and so that should produce that Hamming distance. Okay, and then for the last part, I type out my received vectors, vectors in different rows. And then I take those and multiply those by H of T, our transpose, our decoder matrix. That gives me the received syndromes. And then, yeah, you could build a lookup table and like a dictionary or something. My version of MATLAB's old enough that I don't have the kind of fancy dictionary that the newer thing does. So I just kind of did it manually. So you see here that these are the received syndromes. So then I just look up that like anytime there's 0, 0, 0, then that means that it's there's no error, right? So so I just copied that code word in directly. But if you have that as a particular syndrome where you're looking at 0, 0, 0, that'll come automatically, right? So here, this is just kind of a manual. I'm looking up the error vector that corresponds to these syndromes. Syndromes should have a 1-to-1 correspondence, at least for the minimum weight versions of it. And then that gives us our error vectors, and the error is saying where that error position is. Okay, and then we can multiply or we add that, and you could use an X or there, but we add the X, the error to the received bit, and careful to do our modulo 2 operation that corrects it. Okay. It wouldn't necessarily correct it if we had that minimum weight 2 one there, because that would detect that there's an error, but because it's not a unique 1-to-1 relationship, we wouldn't be able to tell exactly which bits were done, right? So it's common that codes can correct 1 bit and detect maybe 2 bits of errors, right? So generally codes can detect more than they correct. Fancier codes, longer codes, lower code rates can correct more than 1 bit. You know, bigger your code, lower your code rate, the more bits you can correct, but you can generally detect a few more. But we just don't know which ones were wrong. So that's real quick. I'll go back over that and double check it. I just did that real quick. Apologize for that. But I'll touch it up, and then I'll post that, and then I'll organize all that into solutions. And I will be posting a new homework assignment to Kirby source coding and something on this noise figure analysis. So have a great Easter, whatever you celebrate, Ramadan, all that fun stuff. Passover, I don't know when Passover is. It's today. Oh. Okay.
Whatever you want.